Well, we're coming to the last talk, and this is being given by Arieh Warshel, who is a professor, distinguished professor of chemistry at the University of Southern California. And I see that his work he has pioneered the field of computational enzymology, helping develop computer simulations of the functions of the biological systems that have allowed scientists to understand how life processes go ahead. Now, Arieh has quite a few prizes, and got the Nobel Prize a couple of years ago. I'm delighted that he is now here to present his work. Therefore,
Okay, it is a great pleasure to be here. I thank the organizers, and I also thank the two previous speakers that gave me excellent chance to present complementary ideas. So I will try to talk and focus on the challenge in enzyme design and also something related, which is fighting drug resistance. Now, in principle, to wait a little. Okay. It needs time here. Okay, there is a very nice movie of cell signaling, and if you understand the activation and control of the cell, you understand the most important part of biology. It looks very challenging, it is very challenging, but if you dissect it to parts, we are dealing with the action of proteins, and many of them are enzymes. So for the two people here who don't know what are enzymes, these are molecules that bind different substrates and do the chemistry of cleaving them. The puzzle in enzyme, there are several puzzles, but one of them is why enzyme works many order of magnitude faster than the same reaction in solution. And to change the issue of Arnold, basically understanding enzyme does not mean the understanding of their design. I will come to it several times. However, a lot of people do not believe that you understand enzymes or don't understand your computation, don't believe it, unless you are able to predict. Like people start to buy the book Principia only after the Halley comet came back. So, you have to convince people that you could do things. If you try to predict rather than to take the known enzyme, to predict how to design an enzyme, at present the results are extremely disappointing. I will explain later why. And one of the problems in computational enzyme design has been that most of the designers never had a program or ability to take a known enzyme and to explain how it works. So despite, just a second. This is water. So despite a very large propaganda, most of the success in enzyme design, I would argue all of them, were done by directed evolution and not by predicting it. And I have been arguing that this is because these predictions did not include the ability to take a known enzyme and to explain how it works. So we will try to address this issue. And another issue that I will address is the issue of drug resistance, which you will see have some similarity in terms of the challenge, where you start with a drug that works very well. After a while, a new mutant, sometimes very fast, arise, and the drug is not effective. So you want to understand how to predict the mutations of the pathogen and what to do about it. Okay, now in enzyme understanding, not yet design, you want to understand why the activation free energy for the given enzyme and the given substrate is much lower than the corresponding barrier in solution. And at least my, let's call it, conclusion is that the only way to do it is by computations. Because you have extremely complicated system, many interactions, and it's just too difficult to understand it experimentally. The first steps in these directions were to just model proteins or enzymes, which started with simple ball and springs model, force fields with parameters taken from experiments. A lot of work, okay, let's just show the terms. A lot of work was done with Schneur-Olufsen, whose name was mentioned here before, and with Michael Levitt. And the programs that emerge allow you to simulate the, the motion of the protein. But we are dealing with chemistry, and this took a small while, and then emerged the approach called QMMM, a combined quantum mechanical molecular mechanics, which, realizing that you cannot do quantum mechanics or quantum chemistry on the whole enzyme, describe most of the enzymes by ball and springs and residual charges, including, of course, the water. I will come back to the water, and the active site by quantum mechanics. Now, this approach in general is what is called multiscale modeling, which means that at a given time, you have to decide which part you could model by direct computations and which you want to describe by simpler approach, still capturing the physics of the rest. So this is a general direction, and I will focus now only on the action of enzymes. And here you have a challenge. It's not enough to run some quantum mechanical programs, few snapshots, and to believe that you will get correct activation free energy, not enthalpy, of the enzyme. You have to do a lot of simulations to get the right statistics. And this means that the approach has to be both reliable and very fast. You have to combine both of them. And the approach that up to now is by far the most effective is what is called the empirical valence bond, which look to some like high school chemistry, but basically you have force fields for reactants, sometimes intermediates, sometimes products. You mix them to reproduce reality, which is the activation barrier in solution. And then when this is well calibrated, you change the environment from water to a protein. And we have countless examples. I always show this one. We spend a lot of work with GTPAs, which work in G proteins in many signal transduction and other key processes. Very similar is also ATPAs. You have GTP, and you want to perform the chemistry of it with another protein that makes the protein work faster. So you have to know chemistry. It's very complicated because you have high energy excited state. In recent years, it appears that even more complicated because you have, at least in water, extra water operating. And to really understand it, you must run ab initio QMMM. Maybe this movie also doesn't work here. Oh, maybe. Okay, this one. So this is very long simulation of the hydrolysis of GTP with magnesium in classical water. The main issue, of course, is not the movie, but the ability to produce free energy surfaces in water, and then you transform them by simplify EVB to the protein, and you could run the chemistry in the protein. Here, it's some earlier simulation. It's some extra work, where we're supposed to have water molecule attacking magnesium help and hydrolysis. The main point about it is not this movie, but that we produce the observed catalytic effect, which is enormous, 10 to the 8, of these enzymes or related elongation factors, and we could understand how it works. And in this case, there is a recent, I keep working on it, so every year there are several papers. So this is PNAS that shows that EFTU and EFG are working by allosteric effect, that what happens is that the protein changes the structure due to the activator, and then we have lower activation barrier. So we have this tool, which I will use to argue that we know how proteins work where we know the sequence. And from the many proteins that we study, we concluded that every protein that we look at work by electrostatic effect. Now, it's very different than the binding that we heard in the first lecture, because here the substrate, both in the ground state and transition state, is inside the protein. And when we talk on the allosteric effect, so on the electrostatic effect, what we find, and it will be needed for the design section, is that when we have chemistry in water, when we move minus from one atom to another, the water have to rearrange, and this costs reorganization energy, which was formulated by Rudy Marcus. When we go to the protein is already orient its dipoles in a way that we have less reorganization energy and smaller barrier. So large part of the catalysis is due to the fact that in water we have to rearrange the solvent, moving to the transition state. In the protein, we already have pre-organized environment. And by the way, these dipoles could be dipoles of internal water. The main point is that they will already point to the right direction, at least in part, when we are ready for the reaction. So one concept that we will talk on the design is our interest in getting pre-organized environment. The other concept, with the computer, we could also check a lot of proposals for enzyme catalysis, and of course, most of them are wrong. So I will take just one of the wrong one, which will be relevant to the lecture. And this is the desolvation idea. The idea is that in water, if you have a charged residue, it's very stable. When it moves to the active site, it becomes unstable. And this is what leads to ground state destabilization. We are closer to the transition state, and we have to pay less energy in doing the chemistry. Of course, it is incorrect. And it grew up from the finding of organic chemists in the 70s that a lot of reactions which start with charge or polar ground state are faster in non-polar solvent. So since they assume that enzymes are non-polar, this looks like the right explanation. The mistake was that the comparison was incorrect. If you have reactions with charged ground state in benzene, it will be very fast. But the part missing is moving from water to benzene, which will make this dissolution not so useful. So we have two issues to remember in the enzyme design. One is pre-organization, the other problems with dissolution. And I will show you that dissolution is the first move of directed evolution. So directed evolution is not so smart as one would like to think. So we move now to directed evolution and start with a point that I want you to note, that when we take known enzymes and known mutants, where the structure is at least approximately known, we are able to reproduce, this is Christmas mutants, we are able to reproduce the catalytic effect. So if we are so smart, we should be able to design enzymes. So one would like to think. This is another enzyme, also example of something that grew up trying to eliminate chlorinated ethane. And again, we get very nice result. So we decide to see how well we could do, let's call it predicted directed evolution. And we choose the enzymes that everybody, of course, except us, was able to publish in Nature and Science. And this is Camp eliminase. A lot of the hype on this enzyme was because of incorrect analysis of the catalysis. Instead of comparing to a reference state with 55 molar proton acceptor, they compared to just being in water in 1 molar and got very large catalysis, which is not real catalysis. The reaction is this. You have proton acceptor, and then this camp compound is broken. You have oxygen here, which is very important. So we took series of experiment. I think the first stage, most of them were from the Antarctic, and we showed that we could kind of reproduce with kind of known sequence the effect of, I think, the upper one. Yes, this is in water probably. We could reproduce it in another paper where we add catalytic antibody. We did even better, but in all cases, we knew what is the sequence. And one interesting thing that we found is that this enzyme, I did not tell you enough, but enzyme does not work by destabilizing the ground state. It does it by stabilizing the transition state. And we show it by countless examination of different cases. This enzyme have here this proton acceptor acid. Now, obviously, if you increase the pKa of this acid, it will make the reaction faster. So directed evolution, the first thing that it did, it removed water from the active site, increased the pKa of the proton acceptor, and made the reaction somewhat faster. Now, this is a trick which is almost never used in biology because there is a problem. All the acids are in the range close to pH 7, pKa close to 7. There is not much to do with it. So since a lot of people believe in ground state destabilization, we mention that this is just a strange case and we don't believe that enzymes work in this way. Of course, later, Don Hilbert continued with directed evolution and found catalytic antibody which work faster than the original series. And while the first series work actually by ground state destabilization, by taking the water from the active site, the Hilbert compound behave like real enzymes and start to put, in this case, glutamine near the oxygen which is being broken at the active site. But it took a lot of effort, and essentially one thing that we notice a little late is that in one stage of the directed evolution, you already have glutamine, but the distance to the oxyanion is larger than in the last step. So up to this stage, everything went very well. We took all the steps in the directed evolution. And what we are doing here, we don't try to predict directed evolution. We take its results and try to see if our computer gets the same catalysis. And looks very promising. We have reaction in water. The difference here is because of using different reference, but we got all the directed evolution pathway. Everything looks nice. We could get the structures. This is the slowest one. Middle one where we already have the residue which is supposed to be pre-organized, the glutamine. And we have the last step. By the way, we suggested already this glutamine in our first study. And when Taufik and co-worker tried to do a mutation there, it did not help. Okay, so after doing it, we decided to do one more step to see if we could go, since the active site is similar in these two cases, could we move from here to here, which is almost 7 mutations. And here starts the challenge, the real challenge in enzyme design. It appears that while we could perfectly predict for a known structure, or for approximately known structure and sequence, we could predict the catalysis, which means, by the way, that we could understand any relevant biological questions, because the issue is not the design, just to make a point. We cannot, at least up to 5 months ago, move from structures where we already have the correct active site, but the distance residues are not oriented correctly. And now, just to remove possible mistakes, if you have distance mutations, and we know about it, and it is a single mutations, we could easily, or with enough work, get the catalytic effect. What we could not is to move when there are several mutations. And here we took a break, first to fight with the referees, then to rest. And we now try normal mode approach. Originally, we thought that this is a complete disaster because you have to run on all sequence space, and this is impossible. But there are encouraging development in terms of trying to find by normal modes how to do it. But it is a major challenge. Now, since we have to continue to publish in this field, while actually trying to solve the problems, we did simpler exercise. This is called reversal. We took these dihalogenas, which we could model very quantitatively. We could also model mutants of this enzyme very easily. and we try to destroy the active site pre-organization by mutating it to be slower, and then to see if we could go backward. Of course, this type of approach was done a lot by experimentalists, but here you want to see if the computer could do it. And let's see. And we succeed, at least in one case, with biochemists from the Czech Republic. We succeed to destroy the enzyme and then to make it work again. Another revertant become, what is this? Fire alarm. Okay, so now, what is this, fire alarm? Seva Adon? No. Okay. Okay, so we continue faster. So now we go to the other challenge. Do we have to? This is drug resistance. A major challenge even for experimental approach, because you do not know what will be the next move of the virus in response to a new drug. So we try to make it more than computing. How could I forgot the name, how could the virus or the enzyme unbind the substrate? And we know, we just invented, there is what is called vitality, which is the ratio between the ability to bind for the given mutant and the fact that the enzyme of the virus has to do its own chemistry. So there are residues that just would not change. So we have to combine the ability to calculate enzyme activity and mutations, which we have, with the ability to calculate binding that we do as well as other people, which is good but not good enough. So this is cycle of binding. You heard about it. We take special care of water. For binding, you really have to do it. And for inserting the right water. Now, this is very visible field, but there are problems. To know how to insert water correctly, we have a rigorous approach called Grand Canonical Monte Carlo. It's an approach which is basically insane. You have to try to insert water from the bulk to the active site and to reject any failure. And most of the attempts are failure, so it takes a huge amount of time. And we invented an approach which we call water flooding, which actually does the statistics after evaluating the energy of water molecule in the active site. And this approach, which is a factor of 10 to the 5 times faster than the Monte Carlo, but we have to do both of them, gives basically the same result. So we are basically the only groups that validated fast approach by comparing it to the rigorous approach. It's slightly unknown, but it's at present by far the best approach, and we could use it in binding calculations. Now we are still not doing good enough, but let's see how it works for vitality. So the first attempt was with HIV protease. You have to calculate the binding of the drug. Then you have to calculate the binding of the transition state to combine them. Large vitality means that the pathogen will not be too impressed. So this is where you will try to mutate it. Low vitality means this would not be used by the drug. And one finding that is confirmed by experiment, we found that charge groups will not be mutated in HIV protease. We tried this. This is more extensive study. it's kind of not perfect by far. More recently, we try another HCV system. Here you will see more the problems. When we calculate, what is this? Yes, this is the activation barriers. We are doing very well. These are binding free energies, also look good. Unfortunately, when you combine both of them, you get this trend, which means we go in the right direction, but not good enough. And there is also the question, how would you do it, for all possible mutations? And we have ideas. And typically, if you talk on challenges, these are problems that I keep doing for 15 years. I mean, we never leave them. So, but the next generation, of course, should continue. So while trying to keep students doing it, we also look on a new direction, which a lot of people who want job in the industry are very fascinated with. It's called deep learning, big data, whatever. So there is a very important data set in Stanford, which took a lot of years to collect, of many mutants, drugs, and resistance. And when it being studied by this approach, I'm not sure, I will finish soon. What is it? I think this is a tank, I'm not sure. There are different objects there, and this type of software is able to identify and classify them. So the idea is that if we create a grid of the binding interaction in the active site and the catalytic interactions, it will discover it. And what happened up to now, of course, the papers from Stanford train the system on all the known data. So they have 95% success. But of course, it cannot work for any new drug. So up to now, while we are learning it, it appears that there is one advantage, not in binding or anything, but in knowing the sequence, which is resistance. And there is some overlap in this information in the active site, how we call it, transition state binding. So we are not sure, but eventually probably one will have to combine somehow this bioinformatic with computations. And since it's so hard to know what to do just by experiments, this is a worthwhile challenge. These are pictures of people who work with me, and some could find themselves, and I'm thanking you very much. His question was about the theory of RPJ Williams, the Antarctic State theory. The advantage of this theory was that it was never defined correctly. Essentially, I wrote about. So the fact that any attempt to look on metalloenzyme and to look on strain, which was done by computational people, shows that there is no strain there at all. So this was the problem with the Antarctic State, that some people use it to claim that this is the original pre-organization. This is my problem. The theory is that this is destabilizing the ground state was shown computationally to be simply incorrect. There are people of Matt Olson, papers of Matt Olson and others who show quantitatively that it does not work because enzymes are quite flexible. But if you try to relate it to pre-organization, one could show that it was never defined. Anyhow, I have in several of my papers paragraphs. So if you open my paper and look for Williams, you might find the answer.
Any other questions? No, then.
You mean induced dipoles? So as usually, we were the first to introduce polarizable force field in 1976. It included in all the models, and it does not make any. The only difference is that in enzyme, sometimes if you have less polar environment, the polarizability play a role. In water, it plays a very little role because it's either the permanent dipoles are pointing toward the charge or you have extra help from the induced dipoles. But of course, this is included as many other effects. Okay.
Any other questions, please?
No, they weren't.
If not, then thank you very much.
You're welcome.